Okay, everybody. We're continuing on with our discussion of functions. All of the other functions that work on ordered lists of variables have a defined scope, defined set of number of variables in the list that the function works on. With some of these other functions, so I can blow this up a little bit, we have an undetermined number where we have to figure out how many parameters are on the parameter string before we can read the value. The way that this parameter capturing logic works is we have a predefined string parameter called S parameter $, and that holds string values that are separated by spaces. For every parameter that we output, we also overwrite the parameter code value. So for example, if you create a feature-based pocket toolpath, parameter 12780 is the number of tools that are used. So the number of tools that are used in a feature-based machining toolpath. The parameter code would equal 12780, while the S parameter string might have the string character 3 if the FBM operation used 3 tools, or 5 if it has 5. All of the values on the string are string values. It's an important distinction to make. So in order to read them, we also need a method to be able to convert them into real values as well. So we have some functions and this doesn't have all of them. This looks like it's the old list. So I'm looking here for rpar. When we're dealing with these parameters, we basically have 3 different functions. We have a couple different functions we can use. When we're talking about reading individual S parameter strings, in that case, we're either going to use rpar, rpar, so read parameter, rpar sngl, which is read parameter single, or rpar sparam. With these 3 different functions, we can choose individual parameters from the parameter string. We can choose a partial list of variables, or we can start reading at the beginning and tell the function where to stop. So that's an important distinction to make. rpar single will read a single parameter from the string of values. rpar single is the one that I recommend you use if you're not familiar with the parameters, because it's easy to read too many or not enough. When we look in the post and we go to pparam, you can see that this is the default set of parameters that we are capturing from all of the operation parameters that are available. So for MP Master, they have added quite a few different options to be able to read stuff from contour, from drilling, some tool plane stuff, and make that data available to you or control output with that data. This is one of the things in some ways that sets the generic posts from Mastercam, from CNC software, apart. If we just open up, say, the generic Haas 4X mill post, because it's very similar to the generic Fanuc post, and we go look at P param, they're not capturing very many parameters. The logic that exists in the generic posts from CNC software, I mean, it's good stuff, it works, but in-house solutions has added a lot of extra stuff to MP Master, and you can see that for P parameter and also PWRTT params. PWRTT params is where we get data for the tool table. So when we're processing tool table data, we have to read it from P right tool table parameters. If we're processing during normal output, that's where we capture it in P parameter. So it's also important to understand that there are two different parameter post blocks that get called at different times. So if you want something available in the tool table and available in normal processing, you have to add it in both places. So for example, if we look up here during P parameter, as I look down through this list of parameters, I don't see 20,004, 2004, 20004. So if that's the case, if we want to be able to read the 20,004 parameter string, then we can copy this from P right tool table to P parameter if we want to be able to grab that data. In fact, I don't see anything below, in the 20,000 series, I don't see anything below 20,010. So we could do this if we wanted to. You'll notice that here we are capturing the 20,004, the 20,006, and the 20,007 parameter lines. So I'm going to copy those three lines here from P right tool table, and I'll paste them in here. Ooh. I'm actually going to paste them in the correct spot. And the correct spot is to maintain numeric order from top to bottom in this list. Now, you'll notice here, we've got a 12,000 series parameter followed by a 10,000 series parameter. There's nothing inherently against the rules in that. These do not have to be in numeric order. However, I recommend you try to keep them in numeric order because it just will grow out of control if you have this list out of order. It just, once you start getting beyond, a single page that you can scroll up and down on, you don't know if you've added this more than once or not. Now, if we look at these three functions here with RPAR, the form of this line is exactly the same as the form of this line. The differences are the parameter number, the variable name, and I guess potentially the length of the variable name, and the number that comes after the S parameter string. With the rpar function, you'll notice that we have a set of parentheses and a comma in the middle. What this indicates to us is that there are two separate parameters that get passed to the rpar function. So rpar is acting on S parameter, and we are passing the number 1. This is telling us to only read a single parameter from the S parameter string, because many of the parameter values that we're looking at only have a single value. So if we look here, the drill parameters for 5-axis circle mill, we have a parameter 41767. Calculate depth from top of stock option, new for 2017. This tells you what it holds over here, and because there's not a list of more than one value, this is only a single value. For lathe facing, 13721, default Z coordinate. Lathe chip breaking, you notice we've got some 13,000 series parameters. 13710, chip break option is selected. 13711, time in cut option is selected. 13712, time between chip breaks is in seconds. So all of these different parameter numbers are used to grab data from the Mastercam interface. Sometimes we will have parameter numbers that can hold a set list of values. For example, in 10022, this is the old option for cooling, where we hold the parameter number, but it only allows us to read 3 coolant values. I wouldn't use 10,022 because I tend to like to use the new X style coolant. It gives us much more flexibility and many more options for dealing with coolant. But when you see some of these values in terms of a particular parameter number, it's important to know how many different values are passed on the string. If I search for 20,004, there we go. So in the 2017 NCI reference, we have parameter number 20,004, tool definition parameters. And when you look here, under the definition, this tells you how many individual parameter numbers are output on the 20,004 line. We have up to 27 different parameters that we have access to. And then down below, it actually tells us what each of these individual parameter numbers is used for. Parameter number 1 is tool type, tool number. Parameter 2 is the tool type, and you'll notice that it actually lists out the different possible values that we could potentially have set based on the options that are in our dialog. So from 0, which is a custom tool, all the way up to 25, which is a barrel mill. So we have 26 different values because we start counting at 0. This is actually the first one, this is the second one, this is the third one, all the way up to 25. Now this is a perfect example of a place that we could use a string select function to check and see what type of tool type we have and output a string based on the numeric value. So parameter number 2 in this 20,004 list of parameters is going to hold a number from 0 to 25, and based on that we could then choose to output a string by using this functionality. But we're not done. I mean, that's just the second parameter. The third parameter is tool material. And this is another one of those situations where in the guide, they list out the actual values that it could potentially have. So there's only 6 possible values. The important thing to know is that the parameter is going to come out as a number. You're not going to see the parameter string say carbide. The parameter string is going to come out, well, let's look at how it comes out. So if I take this operation, I hit the wrong button. Overwrite and edit on the NCI. And then we go look for the 20,004 parameter string. This is how it comes out. Okay, we have 27 values, in this case numeric values, all separated by spaces. It is important to remember, however, that even though this looks like a number, it is the string representation of the number. So we have to use a function like rpar to do the conversion to a number for us. There are other string functions that work with strings, but if we were to use those string functions on the 20,004 parameter string, that it might not necessarily give us a numeric value. So that's why we use rpar. Now, if we go back and we look at the post, what can you see here about that 20,004 parameter read line of code? How many values is it capturing? That's right. It's the 1st through the 16th. So even though we have 27 potential variables, we're only reading 16 of them. Now, rpar starts at 1. It doesn't start at 0. So it's not a 0-based function, it's a 1-based function. But what we are doing is we are reading parameters from the S parameter string, which looks like this. And we are capturing 1, 2, 3, 4, 5, 6, 7. Remember, it's space delimited. 8, 9, 10, 11, 12, 13, 14, 15, 16. We stop reading here. we are capturing these variable values from the S parameter string, and we are loading them into a list of values that starts with this name. This is the important part to know. Whenever we have an rpar function that reads more than one parameter, then we are reading and loading them into a list that is this many variables long. So we have to go look for this variable slot. And what you'll see here is that we have an array. This is the 20,004 parameter array. So we have a list of values. Now this one happens to be a list of variables that is created with format statements. So we have FMT. You'll notice tip angle and tip angle underscore CH have a prefix string of A, but these are all formatted as real values with format statement number 2. Slot, tool type, material type, corner rad type, diameter, corner rad, threads, tip angle, diameter offset, length offset, tool feed, etc. Okay, so with that single line of code in P parameter and P write TT parameters, we are loading all of these values. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Aha! So this is something to be aware of. Okay, we have 16 values in the list before we get to tip angle underscore CH. This would be the 17th value. So unless we modify that parameter read function, that tip angle CH variable is never going to get set. Now, there may be some other function that sets this value, or it just may be an oversight. I don't know. Now, how would we find out? We find out by searching for the name of that variable. So we know, for example, with the 20,004, here is P parameter. So what I'm doing now is searching for 20,004 because this is how we read the parameter code. We have to set it equal to that number. So I'm just going to search for it. I'm going to remove all my bookmarks. I'm going to add a bookmark here. So I'm flagging it because I know I've been here. Now I'm going to search for 20,004 again. Okay, I'm going to add a bookmark in P write tool table params. It's here on my slot variable definition, and that's it. And in both instances, it's only reading 16 values. So what that means is that unless there's some additional logic that sets the value of tip angle CH, this is basically a dead variable. There's nothing that there's nothing that sets it, so it's always going to be 0. Now, if we search for it, and so here's what they've done. They've added this value at the end of this list, and they're actually using it in a formula. So they're taking the tip angle and they're multiplying it by 2 to get the included angle. So it is used for output, and it's formatted here as A for the angle, but it's not set as part of the parameter read function. Now, they can do this and get away with it. That's fine. It's their post. I would not do this. I would have this as, tip angle included set from tip angle. Because what's going to happen if I try to add more values from that parameter line? Say that I go back to my here and I say, well, you know what? Let's get all 27 values. If I do that, that means that I have to have more variables in my variable list to store the data. Because if I don't, then I'm actually going to end up overwriting the next variables that come after. Okay, so if we wanted to make this, 18, if we wanted to grab the next two values from the list. Now we go back to the list here. Shoulder or shank diameter, taper length. Okay, create two values. Shank diameter, taper length. Taper LEN. So now I can capture those two additional parameters without overwriting these values down here. You got to make sure you don't overrun that table, otherwise you're going to screw it up because it's just going to take these other values and load them into what other variables come next. So in this case, if I made it 27, I'd actually start, so right now we've got 18 variables. This is 19, 20, 21, 22, 23, 24, 25, 26, 27. If I made that 27, we would actually take and put the last set of variables in these variables here from that list. And that's not something we want to do because this is intended to read the 20,006 parameter line. Let's go back and look at the values here. 20,006 cutting parameters for the mills. You can see 20,005 is cutting parameters for drills. So if you wanted to grab parameters from what kind of cycle you had or whatever the parameters are that you load into the variable values, first peck increment, second peck, peck clearance, chip break, dwell, all of these variables are given to you under the cut parameters of the cycle. So here we're taking some of these pre-existing parameters and we're overwriting their values. And we're renaming the string. Just because we rename the string, it still uses the original predefined variable name inside the post. But what we can also do, instead of worrying about using those values, because this is in-feed depth, right? But in reality, it's going to fill in the predefined variable pec1 $sign. Well, maybe we want to actually name it in-feed depth instead of pec1. If we were going to do that, we could then simply read the parameters from the parameter line. So these peck clearance, chip break, dwell, and that's it. 1, 2, 3, 4, 5. And if we look here, 1, 2, 3, 4, 5, 6. So the only one I don't see up there is the shift, I think. Oh, shift value. So it's the 9th value. Okay, so we'd need 1, 2, 3, 4, 5, 6, and 9 if we wanted to grab those parameters and name them something else. It's funny that they actually have this little break with 7 and 8 in between there. 20,006 parameter line has up to 9 values. And you'll notice down below, 8 and 9, obsolete and future use. So really, we can only grab 7 values from this 20,006 parameter line. Oh, look at that. So they're actually grabbing the obsolete and future variable value. Oh, no, sorry. They're grabbing the obsolete, but not future. And now this is funny because here's a case where we're grabbing under cut ability. We're grabbing all of these values. 1, 2, 3, 4, 5, 6, 7, 8. So we've got 8 values that we're grabbing. But if we search for cut ability, it's used here on the parameter read line. It's used here on the parameter read line. And it's used here in the list of values. That means we have no code anywhere in the post that actually uses cut ability. It's simply the start of the list of values that we have in this parameter read line. So we may be using one of these other values somewhere. If we search for step R_XY, it's not listed anywhere else in the post. If we search for step _R_Z, it's not used. Step FXY is not used. Step F_Z is not used. Oh, tip diameter is used. So here in P meta tool, TD_meta equals tip diameter. Okay, so if you happen to have the meta tools backplot utility, now, yeah, exactly. They don't use them, but they have them available for use. So here's tip diameter. That's one that is used. If we look for min diam, it's not. And thread angle, THD is not. So this is the only one out of there that gets used. Now, of course, they do give it to you so that if you want to use the values somewhere else, you can. You can also format them. And the same type of thing happens here with the 20,007 parameter line. We end up capturing a bunch of the values, but we only use a few of them. Yeah, for sure. I mean, there's no reason not to have, not to read all the values when you can, if you want to be able to use this data to do something. Now, there are a couple that have been improved. I think the 20,007 is one of those, because you'll notice now that it used to be, I think, 11 values long, and now it's 13 values long. And the new ones that they've added, tool projection, so distance from the holder, and you'll notice this is the 12th parameter. So the projection down here, 20,007.12, is right here. This is how much is it sticking out of the holder. And then 20,013 or 20,007 parameter 13 is the total holder length. So that's the length here, which means that this overall length from the very tip of the tool to the very holder is not given to us, but we're given 2 values that add up to it. So we can simply add, our own user-defined variable, total OAL, and then add these two together. You notice we're also given assembly name as 20,021. So if we go back and we look at this post, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and we're going to go add I was going to use OOH for out of holder, but it looks too much like zeros for my taste. Notice we over here we have an additional holder length variable. If we go back to the parameter page, you notice it says holder diameter, holder length. Then holder length for X6 and earlier tool definitions deprecated for X7 and later. Parameters 6 and 7 were originally used for the holder diameter and holder length in legacy tool definitions, meaning tools that were created in Mastercam's version X6 and earlier. Tool holders that had been created with the newer tool holder definition functions in X7 and later do not use these parameters. Okay, important to know. These parameters are maintained only for compatibility with older tools. If a tool definition in your part was originally created in X6 or earlier, parameters 6 and 7 will continue to be output with the original values. Otherwise, do not use them. Okay, so we know then that 6 and 7 holder diameter and holder length, if these values are used, it's a bad deal. So it also means if we do a search for HLDRDIA underscore DIA, okay, it's used here in CD underscore meta for the meta tool. All right. And how about holder length? Same thing for the meta tool. Now, I personally have never met a single person that uses the meta tools, so I'd feel pretty confident in not worrying about that. You could always fix this logic if you wanted to. You'll notice this is basically the format of what it outputs for using this this older backplotter code editor thing. You know, it was kind of popular around the early 2000s, but I don't think I've heard of it and anybody using it in probably 10 years. And so now we've got this holder length, and we'll call this holder length. Now, we also have one of those situations where we may want to add another variable that would be the total tool assembly length. I would not just add it to the bottom here. I would create a little separation, put a little comment. Now, this is a case where we could get away with a global formula if we wanted to. And we'll call this like so I'll define it, and I should probably just format it. Here we can also control, based on the format assignment, how many decimals out. 2 is going to use up to 4 decimal places. So you may want to look in those formatting options. Maybe something like format statement number 11, 3 decimal place. Depends on, what you want in your comment. Okay, tool assembly length. And then if we wanted to, we could technically put in a global formula for it as well. Tool assembly length equals tool projection plus holder length. This is one of those cases where it's okay to do this as a global formula because we always want it to be these two numbers added together. We could also do this calculation inside a post block as well and not do it as a global formula. So a couple of options there. Before we go on to look at that parameter stuff, I do at least want to look at miscellaneous values a little bit and want to look at retracts as well. So let's do something here. We had talked about using miscellaneous integers to make decisions. And we've also talked about motion. Do this real quick. Talked about the motion and how do we tell where we're at in the cut. If I post this out with no rotation, here we are at the end of the cycle. And so that we've got 3 off codes for our coolant. If we go look in the post, our motion, G0, G1, G2, G3, for 2-axis and 3-axis machine, is output from only a couple of post blocks. P rapid out, P lin out, P sur out. So this is where we can do some checking with the contour flags to see where are we in the cutting. Are we at the beginning? Are we at the end? Where are we? When we look at how the G code is output, we go ahead and post contour. We're going to go into the debugger. And should expand it. Okay. We'll go ahead and select play. We're paused to answer the question, and we'll let it run. When we look at this output, organize this just a little bit. This is the end here where cutter comp is canceled. So you can see that this is kind of the last move of the contour before we do the retract. The entire line is G01, G40 with a Y motion. And the way that it's built, you can see here it's being built in P-lin out. So here's the output. SG code is what output the G01. And you notice that it's actually a dependent string select value. Why are we using the dependent modifier here? What does that do for us? The dependent modifier prevents SG code from outputting G00, G01, G02, or G03 if there's no other valid output on the line. What it does for us is it prevents us from outputting a line of G code that just has G01 and no X, Y, or Z or rotary value. That's what it does. So this outputs our G01. Then we have the G40. So we have a call to PCCDIA. And if comp was turned on, you notice here, if previous CC pause does not equal CC pause and CC pause, previous tool off no equals C9K. So what happens here is the SCC comp post block, if we or not post block, the string select function, if we look at it, uses tool off no as the selector. And because we're manipulating previous tool off no, this will now output something. That's the logic that controls how we choose to output and where we choose to output the off code. So that's our G40. Then we have our Y line. So our Y output occurred from PY out. This is what actually gave us our Y position. And if we look at the NCI file, you can see here that we have a G1 move. This has got the 140, which gives us our cutter comp off statement. It's got the X and Y position. The X is the same, the Y is different, and looks like the Z is changed. No, Z is not changed. It was minus 0.25 as well. And we've also got this contour flag that says this is the last move of the contour. The next G code, 1004, is a dwell, and there's no dwell present, so we basically skip over. We have a final retract here, which is what causes this output. So when I go and I look at this Z minus 0.05, where is it here? PNC output. This is the line that caused this Z.05. Then we have this rapid move here. So we have the Geo Z10. And this is all controlled based on the actual G code that we have in the NCI. So we have our NCI G codes. And then you'll notice that we have the 1003, which is the end of file. So this is what causes us to call the very last end of file stuff. What ends up happening is a little bit of a trick in the post. So P rapid out and P lin out are going to be what output these moves here. So you can see P lin out and P rapid out are what output the last linear move and the last rapid move here. And then you'll see that we called P retract. So here's PZ out rapid. There's a bunch of calls to P retract. P retract, P retract, P retract, P retract, P retract. Okay, so there's all this P retract stuff. Well, what ends up happening, and there's actually, if you look at it, the output came from PEOF, but the code was generated in P retract. So P retract is a special post block. It is a user-defined post block. P retract, end of toolpath, comma, tool change. Now this is where the definition occurs. There's also P retract 0 for the end of toolpath for a null tool change. This is in MP master. So MP master modified a little bit of stuff in regards to that. P retract, P retract. So this is the definition here, and it is called at the start of PEOF. So here's PEOF with P retract, and it is called here inside P tool change 1002. And if I search again, the only other references to P retract have a 0 behind them. So this doesn't count. That's different. So we've got P retract definition here, and we've got it called once here in PEOF. So I'll bookmark that. And we'll call it again here in P tool change 1002. So you'll notice it only gets called from two places. P retract gets called at the end of file. So at the end of file, First thing we do is we call p-retract. P-retract is used to do a couple of things. It is used to turn off the spindle. It is used to turn off coolant codes if they were previously turned on. And it is used to determine if we need to force a machine Z retract. So again, we call it at the start of the end of file. That means in our case right now, the 1003 G code is what triggered the call to p-retract. The only other place that p-retract gets called is in p-toolchange 1002. So what is p-toolchange 1002? P-toolchange 1002 is not for force tool change. The force tool change switch only does one thing. Okay, so here we've got a case. Got op2, we got op3. Okay, so we post this out. Here's the start of operation 2. Now we get a Z10 and we get operation 3. P-toolchange 1002 was still called in here. P-toolchange 1002 gets called at the start of every single tool change. Call at actual tool change, end last path here. What P-toolchange 1002 does for us is it allows us to make decisions about whether we want to retract or not, and whether we want to perform parameter read type stuff. Now there's another post block that ties into that, which is p-tool-end. So p-tool-end gets called at the end of the toolpath before reading the new tool data. So this is important. If you want to save anything from the last toolpath, you need to do it in p_tool_end. Then p_toolchange1002 gets called. Toolchange1002 gets called with the toolchange aft strategy on the actual NCI G-code toolchange. Toolchange aft strategy reads the first toolpath move after the toolchange with the NCI G-code, and then calls the normal toolchange post block. This prevents skipping information on the first move after a toolchange. So what ends up happening is we read a line ahead of the toolchange to get the next move data. We back up and we call p_toolchange1002. And here we do a bunch of calculations for the toolchange. If op ID does not equal the last op ID, we call p_set_machine, so it sets the rotary switches by reading the machine definition parameters. This gets called for every tool change, so it gets called for the first tool change, the next tool change, and so on. We call p_spindle to calculate spindle speed values. This is where the calculation occurs. We set what line equal to 4, required for the vector toolpaths. Now, we look to see what type of tool change we are processing. If G-code equals 1000, what type of tool change is it? Trick question, because it tells you right here. Null tool change. G-code 1000 equals null tool change, and the only thing that we do is set the command variable uninhibit probe. So if we're using the probing, it triggers some probing stuff. Else. What are the else conditions from G-code equals 1000 for a tool change? There's only two other tool changes it could possibly be. Either a 1001, which is the start of file, or a 1002, which is an actual tool change. So if we're at the start, we're going to hit the else condition, which is true, and then it looks to see if the G-code is equal to 1002. So this else condition gets called for every tool change and for the start of file. Now, when we're at the start of file, G-code is not equal to 1002. It's equal to 1001. So this gets skipped. We still set these though. If stage tool equals 1, previous next tool equals M1, previous XIA equals vector equate X home, previous feed equals C9K. So this is telling us we're going to output the feed move, and this is giving us the previous position for home for the incremental calculations. So this is for incremental, and this is for feed, and this is for stage tool. So basically at the start of file, very start of file, we only execute these right here. But for every other tool change, if the G-code equals 1002, we call p_retract. This is where p_retract gets called. It gets called from the tool change event. So what this allows us to do is capture values in p_tool_end, then we call p_toolchange1002, which actually causes the retract from the last toolpath. It's important to know. Okay? So what ends up happening, we call p_retract. Oh, I didn't set those. Okay. So in p_retract, we call phsm off. We save some values. Save absync equals absync. Then we set absync equal to 1. What is this doing for us? What does absync equal to 1 mean? Right, turning on G91. So we're in incremental mode. So we're saving the current mode. We're setting incremental. That means the next time that we see SG absync on a line by itself, we're going to output G91. Save coolant equals coolant. Coolant equals 0. We just shut coolant off. Okay, we just shut the flag for coolant off. So now we execute the code that looks to see what type of coolant we have on. If all cool off, if that switch is on, we execute here. Otherwise, we execute the else case. And what this does for us is looks to see if we have coolant turned on with canned text, which is the new style of coolant. And it uses this local int to parse through all of the coolant values, and using this binary function AND, we look to see if coolant has been turned on. And if coolant has been turned on, we turn it off. So that's what this little bit of complex logic here. It's only a few lines of code, but it's actually really complex what's going on here with this while loop to turn off all the coolant codes. So this is where all the coolant gets disabled from. Then we set CC pause equal to 0. Convert rapid is 1. We set G code equal to 1. We set feed equals maximum feed. We set IPR type to 0. Else, G code equals 0. So what we're doing is we're setting all of these modes just prior to where we have this output. How can we tell it's output? Well, it's got that common output post line signature, PBLD, comma, and $, comma. Okay, anytime you see a line that starts with PBLD and $, it's typically an output line. You'll notice it ends with $. So here's where we output comp off and turn off the spindle. Okay, we force out MO5, and if we're in a subroutine, we end the subs. Then we have a line of code that forces the Z on our machine to retract to machine home. At least that's what it's supposed to do, right? G91, G0, G28, Z0. And if we're using X or pre-X style coolant, version 9 style coolant, we turn coolant off here. You notice there are some options here that we can enable. They are turned off by default. Lock and unlock codes. X0, Y0. So returning G28, X0, Y0, and also returning rotary to 0. If we want, we can output that. We can also add logic to control when we do this here. Okay, now if we wanted this, we wanted to be able to control it, I would probably put in something like a flag variable, if we're at the end of file, output, go home in X and Y as well. So all of this stuff happens, and then we restore the absync and the coolant values. So this is where we go back to G90, and this is where we set the coolant back to where it was set. Okay, so I wanted to point that out. That's how this mechanism works. P-retract gets called by P-toolchange 1002 to kick off the next toolpath that's coming. Okay. this is the wrong post anyway. It's not the post we're actually outputting with, which is this one. So what about P retract 0? MP Master has a common tool change post block. P tool change common. And this gets called at the end of PSOF, and it gets called at the end of P tool change. The other tool change event that we have is null tool change. And in MP Master, there's a lot of logic that's in null tool change because we're trying to look and see what has changed. Are we just picking the tool up and moving it over and making another pass, or are we rotating? And yes, P, so you'll see here, there's actually some complex logic in here, okay? Tool change 0 equals 1. There's a flag variable that indicates we're in the null tool change. We check and see if the op ID is different. So are we processing a new operation or not? If it's a new operation, we read the parameters, we check, we do the pmisc check. We call p cut type. So we calculate all those cut type related stuff, all the positionings, all that stuff gets calculated. There's a ton of stuff that gets done just from this one call. Then we return. Tool count equals tool count plus 1. If tool count n is less than or equal to tool total, next tool equals read buff for tool count n. Else, next tool equals first tool. We set retract flag to 0. Then we come across this mouthful of a Boolean logic statement. We have 3 conditions we are testing for. If this condition or this condition or this condition is true, then we do all this. Okay, so what are these conditions? If MI10 and op ID does not equal last op ID, or op ID equals last op ID and xform op ID does not equal op ID. So we're checking to see if we're in a transform toolpath and we're doing a new version of the transform, or if we're simply doing a new toolpath and MI10 is turned on. MI10 being the trigger here. MI10 must be turned on because of the AND condition, regardless of whether any of this is true. So if we go look at MI10, MOO before operation, yes or no? So if that's turned on, and one of these 2 conditions is true. So we've got this and this, or this. So one of these 2 conditions is true, and MI10 is turned on, then we execute the code that's in here. Or tool plane number does not equal the last tool plane number. What does that mean? That means that the tool plane has changed. So even though we're using the same tool, we've rotated the tool plane. Or rotary type does not equal last rotary type. Okay, so maybe the last operation was no rotation, and this current operation is axis sub. And RET on INDX. So if one of these conditions is true, either the tool plane has changed or the rotary type has changed, and this switch is turned on, then this is true. So we have to check the value of retract on index. Okay, machine home retract on rotary index moves. Yes or no? It's set to yes, which means that if this is true and one of these two things is true, we're golden. It's going to jump in here. The final test has to do with the value of MR1 and MR2. And these control the high-speed codes. Now, one of the reasons I really like MP Master is that they have put a lot of time into figuring out the logic for controlling high-speed modes and knowing when to turn stuff on and when to turn it off. You basically select your high-speed mode here with MR1. So we've got the G08, we've got the G05 with number 2, we've got the HPCC with number 3, and we've got Mazak with number 4. So we turn on our high-speed mode, and we set our acceleration deceleration value. So for G05, Q1, and G66.1 only. So it's basically only for mode number 2 and mode number 4 do we use MR2. So I'm going to set that to 2. We'll set this to 7. Oh, and you know what? We wouldn't actually want to do that because this is a drill. We would want to go to contour, and we'll go miscellaneous values. Okay, I'm going to set it to 2 and 3 for this contour. And this contour, I'm going to set it to 2 and 9. Because we've changed miss values, we need to force a regen. You always want to force a regen for that. So we'll output that, and go for the drill cycle. We come to our first op here, and we get our high-speed code. Now, what do we have in between? We have a null tool change event. But look what happened. Because the value has changed, we actually output G05.1 QO to turn it off. We retract with G91 G28C0. We call up op3, and because we've set a flag internally to realize that we've forced a retraction, we output all this stuff all over again. MP Master does that for us. The generic Fanuc post from Mastercam does not. And because our value changed, we output the new value. Now, what happens if the value doesn't change? This is the beauty. This is the logic that they've worked out. So if we go back here and it's 2 and 3, which is the exact same value that we had for operation 2, so now, look at this. It totally changes the retract behavior because nothing changed as far as the accuracy goes between the two. So they've got this beautiful logic in there that checks to see what has changed, and if it needs to, notice if MR1 equals 2 and op ID does not equal last op ID and MR2 does not equal the last MR2, we turn the HSM code off. If MI10 is turned on, we output this stuff right here. Else, we do P retract 0 and we set retract flag equal to 1. Okay, and if this condition isn't true, if none of these things are true here, we still check this else condition. And it says if MR1 does not equal last MR1 or MR2 does not equal last MR2, PHSM off. So we can actually shut off the high-speed code from one operation to the next, even through a null tool change. Now with this retract flag, here is further down inside P tool change 0. So this is what turned on the retract flag. If we have to retract, this is what flags it. And then later on down here, if retract flag. So here's the code that outputs the safe approach move after we've forced the retract. And then we call the high-speed mode either before or after the tool length comp. Depends on what mode we're using. So they've got all this really great logic built into the post to control the output of the high-speed codes, the changing of the high-speed codes, and shutting off the high-speed codes where necessary. Okay. All right, guys. It is getting late for tonight, so I think we're going to wrap up the rest of the class. I think I will try to cover maybe just another hour on our very final night as our final makeup for not being here on time. So I'm planning for that. I'm thinking probably Wednesday of this coming week, either Wednesday or Thursday. Does anybody have a preference either way between those 2 days, Wednesday or Thursday? Cool. Thursday's fine by me, man. We'll do it Thursday. Cool. Thanks, guys. So we'll do a final wrap-up of the class coming up this Thursday. And I will work to get Derek to put up all the class videos and make sure that we've got all the office hours stuff up there. I'm also going to work and see... Oh, let's do this.